Okay, so I got 20 minutes plus questions, right?
20 minutes plus 10, yeah.
Okay, I have 15 slides, 14 slides. Well, thanks very much to the organizers. My group has been doing recently a lot of experiments trying to measure the charge fluctuations in strange metals. As all of you are aware, neutron scattering has been sort of foundational in the field of high TC, and neutrons measure the finite momentum spin fluctuations and have been responsible for a large part of the phenomenology of the materials. All the pi fluctuations, some of which are incommensurate, the hourglass and all that. So we've been trying to do the analogous thing for the charge fluctuations, and we have new data that's particularly relevant to the strange metal, and I wanted to show it. I actually was not originally on the program for this meeting, but I saw the announcement, and so I just registered to show up because I don't understand our data, and I just wanted to get some help. And then Shimao emailed me and said, your talk is at 3, send me a title, and so I made a talk. So thank you very much. I would have been happy with a poster, but okay, so I'm going to describe. So just for those of you who need to leave and leave before the end, basically the density fluctuations in a strange metal look like those of a complex fluid. And by a complex fluid, I mean something like liquid water. The dynamics are relaxational, and they exhibit a phenomenon called DeGennes narrowing, which is something that happens in things like cholesterol, polymers, other structured liquids. Actually, one of the first X-ray experiments I did as a grad student was measuring DeGennes narrowing in water. So, and I don't know why a cuprate would do such a thing, but I'll just show you what we get. So this meeting is about strange metals. So the phenomenology is fairly simple. They have T-linear resistivity, which is hard to get out of a Boltzmann transport quasi-particle scattering model. The resistivity violates the Mott-Joffe-Regel limit, which we heard a little bit about from the cold atom people. And the dissipation is Planckian. Now, I don't know what Planckian means, and I don't think anyone else does either. But it means that it's somehow there's a KBT over H bar with some numbers up front that don't deviate by more than a factor of 10 in scattering rates. So I'm going to show you that this is not only consistent with what's seen in transported, but it carries over to the charge fluctuations as well. There are many other properties that may or may not be strange metal. They have non-Drude conductivity, linear omega lifetimes in the ARPAs, and so on. And so I'm not going to get into all those. I guess it's already been discussed. Is a strange metal even a thing? We're going to set that aside and just talk about the data. Okay, so one of the things that I've already heard a lot of today is that it could be that you can account for the properties of strange metals in a rather simplistic way by assuming that you have simple quasi-particles, but they behave unusually because they're coupled to some anomalous bosonic continuum of fluctuations. And there's a paper by Steve Kivelson that he's emailed to almost everybody in the country that I didn't realize was not on the archive. But the idea is what they do is they just assume they have a spectrum of two-level systems, and they start with a plain old Fermi liquid and they couple the two, and they assume some distribution in exchange values, and what they get out is T-linear resistivity. So this is a fairly new result, but I wanted to point out that this harkens back to some things that were discussed a lot in the late 1980s, early 1990s, which was this thing called the marginal Fermi liquid hypothesis, which I was glad to also hear a little bit about today. And this came from Chandra Varma and Peter Littlewood and Abrahams and others, and the idea was they just postulated the existence of some kind of bosonic continuum. And this is what and it was basically linear in omega up to the temperature and then constant after that up to some cutoff. And they showed that if you postulated that this continuum exists, you could explain almost all the properties of strange metals, the T-linear resistivity and the NMR relaxation rate and the conductivity, frequency-dependent conductivity, and many things. So it's a sort of interesting experimental question to ask, does a continuum like this exist? We should be able to measure it if it's there. And one of the most bizarre properties of it is it's supposed to be independent of momentum. So the way you kill quasi-particles everywhere on the Fermi surface by invoking a continuum is that continuum needs to be present at all momenta. And Because if it's some kind of dispersing excitation like you'd get in a Fermi liquid, then it's not going to act everywhere on the Fermi surface uniformly. So this is an experimental question. So does this Q-independent continuum exist? And if it does, can it explain the bizarre properties of strange metals? Okay, so you can get some early hints simply by looking at the optical data. So this thing I've called pi here is the polarizability. That's related to the dielectric constant. It's 1 minus v pi. You can measure that at q equals 0 with optics. And when you do, and by you I mean Dirk van der Marel and Tom Timmusk and many other people, what you see is a plasmon. Depends on how you plot it, but if you plot minus imaginary part of 1 over epsilon, then there's a peak. It sits at a plasma frequency of about an EV, and it's got some strange line shapes. It doesn't shift with doping the way you would expect, but there is a collective mode there. That's what you would get in a Fermi liquid too. But the question really concerns what happens in this system at non-zero momentum. So is there something frequency independent present or not? So that's what we've been trying to find out. The technique we've been using is EELS. So we've developed a new brand of surface reflection EELS. We've been calling it EELS just to emphasize the fact that it's fully momentum resolved the same way you get momentum resolution in triple axis neutron scattering. We do it with this using eucentric goniometers. And basically what you do is you shoot an electron at a surface. The surface has to be prepared in the same way you would do for photoemission. And then you measure the scattering cross-section. And the cross-section is some matrix elements, which you can write out analytically in a reasonable approximation, times the density correlation function of the surface. So that's just the spectrum of fluctuations. And this S is related to chi double prime. That's the charge susceptibility with a proportionality constant that's a Bose factor. And you can then, so S is what you measure. What you'd like to get is chi. That's the thing that tells you what the excitations do. And you can get chi by anti-symmetrizing the correlation function. I'm going to show you some of that in a minute. And I'd like to point out an important property of chi. So chi double prime actually has this exact form. And if you consider the case where the excitations are momentum independent, then this thing is just minus imaginary part of 1 over epsilon plus 1. So you'll see if you open old textbooks on EELS and also if you talk to people who do surface TEM, they'll say that their EELS measures 1 over epsilon plus 1. That comes about if you assume this thing is momentum independent. But if it's momentum dependent, then you just get a different response function. I only bring this up because I'm pointing out that we're basically measuring the infrared optical response of the material. And it's actually a bulk probe. It's a reflection technique. You measure it as surface, but what you're measuring is the bulk excitations of a semi-infinite system and not strictly a surface excitations. Okay, so good. That's 8 minutes. So every time I give a talk on strange metals, the first thing people ask is, have you ever done an experiment on a Fermi liquid? Because they usually think there's something wrong with the instrument. So I'm just going to go ahead and show you that now. So this is an EELS study from a Fermi liquid. This is doped bismuth selenide. Bismuth selenide is a topological insulator. But if you have too many selenium vacancies so that you dope electrons all the way up into the conduction band, it's basically an ordinary Fermi liquid. And if you do EELS from that, then you see a collective mode, and that collective mode is a plasmon. And the plasma frequency is this. It's Ne squared over epsilon infinity m star. And what we did is we took a bunch of crystals with different dopant densities, measured the carrier density with Hall coefficient, and then you can plot the square of the plasma frequency, which is the frequency of this peak, against the carrier density. You can see that it forms a line. And the line is given by the effective mass, which you can measure with photoemission. So it all works, okay? So no matter how weird what I show you from now on is, you can be sure it's not a property of the instrument, it's a property of the material. Okay? All right, good. So what I'm going to show you is data from bilayer BISCO. I now know from the previous speaker we need to be looking at trilayer, but I'll come discuss that at the question period. At any rate, so I'm going to briefly flash different dopings, which we've published data from, but I'm going to focus on the optimally doped material, which is the one that's really strange in the sense that the resistivity is T linear all the way down to Tc and up to above the Mott-Joffe-Rego limit. Okay, so here is the first one way of looking at the momentum data. So this is a zero frequency momentum map using surface EELS of bismuth 2212. So this is the analog of a Fermi surface plot in ARPAs. Basically what you do is you look at zero frequency, that's elastic scattering, and then just scan in momentum space to see where all the Bragg peaks are. And you see some things that you expect. There are a lot of reflections in BISCO because it has a supermodulation. And so these are all the supermodulation peaks. You see them also if you take an STM spectrum and Fourier transform it, you see peaks in the same location. So all this works well. By the way, you can think of this as energy resolved lead. Lead is low energy electron diffraction. This is basically a lead pattern looking at only the elastic scattered electrons. And what I'm going to show you are data stepping along this direction in momentum space where we can avoid a lot of these supermodulation reflections. Okay? So what would you like to do? What you'd like to do is start at low momentum and see if we see something consistent with optics, and then go to large wave vector and see what happens out there where all the neutron data show all the really interesting physics. So at low Q, everything is kosher. So you have to be a little bit careful how you compare EELS data to optical data. But basically, the comparison is here. So what's shown on the left are a set of EELS spectrum. So the points are the actual data. I'll tell you what the lines are in a second. And these are done for a series of momenta. So this is an energy from energy 0 to 2 eV, so the plasma frequency is at around 1. And then these are different momenta measured in reciprocal lattice units. So if you take 1 over this number, that gives you the wavelength of the excitation in lattice parameters. So this is 100 lattice parameters, this is 10 lattice parameters, and so on. So now EELS measures this funny response function that I showed you earlier, and if I had a really polished talk, I would have emphasized it more. So this is the response function we measure with EELS. It's not exactly the same as the response function you measure with optics, but we can relate them. And we can do that by using a framework developed by Jane and Allen in the 1980s. This was actually for analyzing Raman scattering from gallium arsenide heterostructures. At the time, a lot of history behind that, but basically D naught is the response measured with optics. Okay, so you can take D naught from optical data, and we did this from Dirk van der Marel's data. And then you can plug it in here and calculate the EELS cross-section with it and then compare it to the data. So if you do that, and then D naught, of course, is only measured at Q equals 0 in optics, but you can just say, all right, let's just pretend it's Q independent and then compare it to the EELS data at different momenta and see what we get. And then what you see, so the lines are actually taking the optical data, putting it through the Jane and Allen machinery, putting in the EELS matrix elements, and then plotting it on top of the data. And you can see at small momentum, it agrees pretty well. And this dimple here comes about because there's a plasmon in the optics. So at very low momentum, there's this tail here. It comes from the matrix elements in EELS, which at small momentum are very frequency dependent. But as you go to increasing momentum, you can see a shoulder there, and it agrees fairly well with optics. So this is somewhat technical, and I don't want to put everyone to sleep because it's already after 3 o'clock. But what this means is that we see a plasmon at small momentum. And we see it at the same frequency with the same width as they see in optics. So while EELS and optics measure slightly different quantities, the two are consistent with one another as far as we can tell using just basic electromagnetism. Okay, so there's no reason to suspect the experiment at this point. Okay, so the real question is what happens at larger Q? And you can see what happens. For momenta bigger than about 0.05, you start to see deviation between the EELS data and the optical data. So that if you simply trusted optics to be relevant at all momenta, you'd expect to see a plasmon that kind of disperses. But what the EELS does is it turns into a continuum that's basically frequency independent. So this is best seen so this is at larger Q. This is a Q of 0.18. So this is well out into the Brouillon zone now. And this is plotting now from 0 to 300 MeV. And what you can see is at zero frequency, there's a zero loss line. That's a lead effect. It's from diffuse scattering. There are some phonons. The phonons, by the way, line up exactly where you see the kinks in photomission. Okay? And then on top, then underneath, there's a continuum. okay? And the continuum is flat, very flat. It's flat enough that it really looks quite a lot like this, okay? So how flat is flat? I mean, meaning from 0 to 300 MeV, it looks almost constant. But you can keep scanning. If you go up to 600 MeV, it's still more or less constant. You can go up to an EV and it's still there.
So the way you establish back on the energy loss side?
What's that?
The way you establish.
Oh, yeah, from the energy gain side. Yeah. Actually, the energy gain, you can see the background level, right? So that's 0. So this is real excitations, and it's very strong. This is not some little tiny wiggle in an STM science paper. This is the dominant contribution to the charge susceptibility of the cuprates. 99% of the spectral weight is contained in this continuum. It's not a tiny effect. It is highly, highly reproducible. We've seen it hundreds of times over the last 5 years. So if you keep going, eventually above an EV, there's a cutoff. And then it decays like a power loss. It doesn't go forever, and it can't without violating some rules, obviously. So the relevance to strange metals comes when you ask, what part of the phase diagram has this continuum? And this was published by my student Ali Hussein in 2019, but it basically lives inside a fan region of the phase diagram that's centered on optimal doping. So there is a perfect correlation between a T-linear term in the resistivity and the existence of this continuum. Now, correlation does not imply causation. They could exist for completely different reasons, but they're both, but when one is there, the other one is too. Okay, so what I really wanted to do is show you the low energy data. So if you zip back, sorry, I just made my talk last night and this morning, but at low energy, this thing is supposed to be frequency dependent. And the slope of this is supposed to be given by 1 over T, and that's crucial because that's the part of this that gives you the T-linear resistivity. So we've spent quite a while trying to go down and measure this low energy region where omega is of order T. And by doing a lot of extra work, we've been able to get better energy resolution and momentum resolution, and now we can see it, sort of. So what is shown on the left now is the low energy region. So this is minus 50 MeV to 150. And this is the correlation function. That's what you measure in the experiment. So to get the susceptibility, you have to anti-symmetrize that. But what you can see is something rather unexciting. There's a peak at 0 frequency. And the width of that peak is temperature dependent. Okay, so this is sort of normal diffusive dynamics, relaxational dynamics in a liquid. What you get is a peak centered at 0, and then as the scattering rate changes, the width of that peak changes. So it's a good measure of the scattering rate. Another way to view it is to take S and anti-symmetrize it to get the susceptibility, which will then necessarily be odd. And you can see that that looks like this. And there is the gray shows the region, just to be honest, where the resolution is really important. And I don't absolutely trust the results, but the bottom line is there is a thing in here with a slope, and the slope changes with temperature. At lower temperature, it gets more steep. So it looks like it's consistent with a thing where there's a thing with linear omega slope with the slope 1 over temperature, which was what the original marginal Fermi liquid hypothesis suggested. Let me show you some better data. So these are different momenta now, so we can measure this thing over the whole momentum range, and then it's possible to fit it. And this can be fit perfectly with formulas straight out of Chaikin and Lubensky, okay? Just a solid state physics book. So if you go to the chapter on relaxational dynamics, this is the expression for a correlation function in relaxational dynamics. Just some number times omega over omega squared plus a gamma. A gamma is a scattering rate. And in a system that has relaxation and diffusion, gamma should have just a tau to the minus 1 plus something dq squared. So tau is a relaxation rate, d is a diffusion constant. And so so we can fit the data at all momentum everywhere in the Broughton zone with a formula very close to this. And what you get is, this is the interesting thing, so this is gamma. And gamma is temperature dependent and it's Q dependent. And so red is 300 Kelvin, purple is 50 Kelvin, and in between it changes. So the background tau is quite temperature dependent, so that gives you this offset. And then the interesting thing is there's a minimum at finite Q. So in normal diffusion, this dq square implies that the gamma width is smallest at Q equals 0, and then as you increase Q, it gets wider. And that tendency gives you actually the diffusion constant, okay? So what we find is that this system has such a minimum, but the minimum is at finite Q, meaning it fits this form. And those of you who've done neutron scattering may know that DeGennes wrote a paper in the 1950s on neutron scattering from structured liquids, and what he showed is that they exhibit what we now call DeGennes narrowing, which is a minimum at a wave vector that's dependent on what objects are fluctuating. And let me just explain that for a minute, since I have been disciplined and not wasted too much time. Let's suppose I take some water and I scatter X-rays or neutrons from it. What I will see is a spectrum that looks a lot like this. Water, all the dynamics are diffusive. At very small momentum, there will be a sound wave, but any appreciable momentum, what you get is just relaxational dynamics, because water is a structured liquid. If you measure gamma as a function of Q in water, eventually at large Q, it exhibits a minimum as a function of Q, and the minimum is at a momentum that is the inverse of the size of a water molecule. And now, why is that? The reason is that because water is fluctuating very quickly, but at a Q that's the inverse of this, but a water molecule itself is rigid. So at a wave vector that's sort of the inverse of the size of a water molecule, the fluctuations in a sense are slower because a water molecule itself is static. They may be moving around a little bit, so there'll still be some width, but it will be less. So this was a very mysterious thing, and DeGennes was the one who explained it, which is why we now call it DeGennes narrowing. But it basically means that my fluid, whatever it is made up of finite objects, and those objects are colliding off of one another, and the dynamics is determined by these collisions. So the weird thing is, in this strange metal, we see such a minimum. And what it suggests is that the low energy dynamics in this strange metal state arise from some finite objects that are colliding off of one another. And the flow is dominated by sort of the steric interactions between these things. And you can estimate their size by looking at the inverse of where this minimum is. So let me just show you the fit. So you can fit this thing, get a tau, which is sort of the momentum independent background, and then you can get a d and a q. So d is the diffusion constant, q is just the q vector. And you can get the size of the objects, their diffusion constant, and then a background relaxation rate. And this is what they look like. So tau to the minus 1 is the q independent part, so it's obviously a constant, but it is extremely temperature dependent. And at low q, so 8 MeV is the resolution of the measurement, so it can never be less than that. It always eventually plateaus to some constant because we don't have infinitely good resolution. But if you go to larger momentum, there's something that you can put a line through if you wanted to imagine this thing was linear in temperature. And if you fit that line, alpha is about 0.38. So it is Planckian, at least as Planckian as any resistivity is. And I'd just like to point out that all these numbers are real numbers, okay? So tau has units of MeV, that's actually h bar over tau, but tau to the minus 1 is actually an MeV, and T is temperature, so there's no fitting. You can measure this alpha, it's an actual number, and it's of order 1. I had a debate with my student, is 0.38 of order 1? He said, well, it's less than of order 1. I said, no, it's not, it's less than 1, but it's not less than of order 1. That doesn't mean anything. D is constant as far as we can tell. It's 16 MeV angstrom plus or minus 5. And Q naught is temperature dependent. So this is in reciprocal lattice units, and you can see at low temperature it's about 0.65. At room temperature it's around 0.4. But what it means is that this strange metal is made out of fluctuating objects, but the size of those objects is temperature dependent. At low temperature, at high temperature, there are about 2 lattice parameters in size. And then as you go to lower temperature, they get smaller. And they're, So I don't know what that means, but that's what we see. What's 1 over 0.6? Large Q means smaller real space. Yeah, so in summary, we've been doing surface EELS, and at small q, all the probes seem to agree. There's a nice plasmon. It has to be there because it's a charged Fermi liquid, so the collective mode is gapped. It's up at high frequency. It's not like cold atoms where they're neutral, so everything's gapless. But all the measurements seem to be consistent. But at wave vectors larger than about 0.05, the excitations become coherent, and you get a continuum. And this continuum is frequency independent at large frequency, up to a cutoff of an EV, which is a ridiculously high energy scale for a solid. And at low energy, the dynamics are relaxational. Relaxational means they fit perfectly to the equation you can pull out of Chaikin's book in the chapter on relaxational dynamics. Relaxational means that it's either dissipation or diffusion, okay? So the dissipative part is Planckian. It is linear-ish in temperature with a slope that's of order 1. And the diffusive part has a minimum at finite Q, which is an effect called DeGennes narrowing, which means that diffusive dynamics are dominated by finite objects that are colliding off of one another and propagating in a diffusive way. And the size of these objects is temperature dependent. And don't ask me what they are because I don't know. Though I would like to, now that I'm done, make a plug for my collaborator, Debanjan Chowdhury at Cornell, who actually has a preprint on the archive saying that a lot of these dynamics are consistent with what you'd expect at a jamming transition, which actually in 3 dimensions is called a rigidity transition. A lot of the dynamics are similar. So just a plug for him. Okay, thanks a lot.
Time for a couple of questions, please. Yeah, so I was curious. 2 questions. One, how do you eliminate multiple scattering?
Oh, I don't.
Okay, so you don't. Okay.
Well, okay. Let me put it this way. Let me not be flippant. There is a theory of surface EELS that was proposed by Doug Mills from UC Irvine in the 1970s. He's a very prominent theorist who studies surface science. And what he argued is that in surface EELS, multiple scattering is very strong, but it occurs predominantly in the elastic channel. So in that situation, you can apply what's called the distorted wave Born approximation, where you solve the multiple scattering problem is basically a quantum mechanics problem of elastic scattering just of an electron from a surface. And then he said that the inelastic scattering you could basically describe in the Born approximation. And that agrees pretty well with most of the measurements we see. So that's where this expression for the cross section comes from that theory. So you still measure a linear response function, but it's not the same one that you'd measure if you did an optics experiment. So and the fact that agrees with optical data at small q, which definitely is in the linear regime, suggests we're measuring something in linear response. But I can't prove that there isn't multiple scattering.
So I'm confused by something very elementary. So if I have a diffusion, then I can connect diffusion with the conductivity.
Yeah.
And that's basically a continuity equation. Right?
Yeah.
And now if it's not dq squared, but it becomes d of q minus q0 squared, that means that there's a linear q dependence in that component. So does that still translate to a finite?
No, yeah, it's a good question. So I should have done that. I didn't have time. There should be another minimum at q equals 0. With 2, it goes down, then it comes up, and then it goes down again. So yeah.
So basically, you are still measuring sort of a microscopic part of the response.
Yeah, and then there's a conversation whether those 2 minima have the same curvature and give you the same diffusion constant. They should. But if you do the same thing in liquid helium, you get 2 minima, and one of them they call a Roton minimum.
When you said that the EELS and optics are compatible,
Yeah.
which part of Q were you looking
Small q.
at?
Now, yeah, now here's the thing, at small q, you know, V of q, the Coulomb interaction diverges like 1 over q squared. So you have to be careful how you compare because there's all these plasmon effects at small momentum that come in. So that's why I didn't show you the diffusion constant at small q, because I'm still trying to figure out how to do that. Yeah, but yeah, there should be 2 minima, which is what DeGennes said in his old paper.
Can I follow up? Somebody else's question.
Peter, sorry, elementary question. I'm forgetting my basic response to the electron gas. Should you see a peak at the plasma frequency?
Yeah, at small q.
Right. So
Yeah.
it looks like a small group, which almost a bump on the curve.
This is
It's like a much bigger response. So what?
Oh, speak slower.
Yeah. How should epsilon of omega look like for an ideal electron gas? Shouldn't be omega minus omega plasma squared, and shouldn't there be a strong response? All right.
You mean, what kind of electron gas? A non-interacting electron gas? I'm glad you asked, because Jörg Schmalian, bless his heart, calculated it for us, just because people ask so much. And here it is. I have answers to all questions. This is what you get. So you're saying, let's pretend I have this Fermi surface, and then I take this out of a different book, Mahan or Feder and Walechka, and then I compute that Lindhard thing and I plug it in here. What you get is a plasmon with a plasma frequency of an EV that's a dispersing collective mode like you get in aluminum. That's what you'd predict. But you don't see that. That's not seen in the experiment, at least not our experiments. What we get is this marginal Fermi liquid looking thing.
Would you see it in bismuth selenide, since you gave the example of...
Yes, we do, yeah. Yeah, that's this peak. So bismuth selenide looks like, oh goodness, too many slides, I'm sorry. Yeah, here it is. Well, this is doping dependence. If you look at the Q dependence of this, we didn't have great Q dependence at that time, it was 2015, but that's an ordinary collective mode with a nice, I mean, we change density and it shifts in a way that makes perfect sense, which also doesn't happen in the cuprates. You know, the plasma frequency in the cuprates doesn't depend on where you are in the phase diagram. It couldn't care less how many electrons are in the system. That's already a hint that there's a problem.
Oh, yeah, I was just curious. I mean, Cupid is known to be extremely two-dimensional, right? I mean,
Yeah.
you're basically looking at whatever is within the layer. I mean,
Yeah.
you have to expect that whatever this object you have is going to be highly, dependent on the third direction as well. Be quite different, right? Have we tried that?
Well, I don't know how. I tried what?
I mean,
We just studied.
Yeah.
The system is a 3D system, so I don't have a way of studying an analogous 2D system.
But I mean, you just look at the momentum dependence along the c-axis.
Okay, it's a good point. We don't conserve momentum in that direction. This is like ARPES. So what we do is we measure a response function.
It's an integration of the momentum along the c-axis.
Yeah, it's an integration of Z. We measure this. It's actually very similar to the ARPES. Just people have looked at ARPES for so long, they forget that there's a Z, right? But you actually integrate over the Z. So the chi you measure is a mixed one. It has, the Q here is the in-plane Q. And then it's written as a function of the out-of-plane coordinates, then you integrate. So you have to, so the Jane and Allen, that's exactly what it does, is it allows you to take a bulk 3D measurement and then compare it to this thing. So that's the best I can do, but they do agree it's small q. Yeah.
So for bismuth selenide, did you still get this depth, this minimum and finite q, and were you able to get an estimate for this?
No, because the dynamics in bismuth selenide aren't relaxational. So the gamma, a gamma only means something if it's a relaxational system, meaning all the dynamics are less than there's no energy scale, there's no peak, right, in Bisco at finite Q. Bismuth selenide, there always is a peak there, so there's no gamma to discuss.
Beautiful talk. I saw your diffusion coefficient, and I was immediately thinking, what is that in units of h bar over n, my favorite unit of
This.
diffusion?
Well, I put an h bar on it, anticipating people would like to see. So if I take this and I divide by h bar, I get the d. Which units do you want?
So h bar over the mass of the electron is actually not so far off from from this, I believe. By the way, I think it should be angstrom squared.
It's angstrom squared. You're exactly right. I'm sorry.
It's okay.
I-
But I think it's
Yeah.
interesting that it is not so far off the scale of h bar over the electron mass. And of course, probably we should use the m star and then see whether it comes close.
Why is that close to the resistance?
It happens to be close. I just plugged in the numbers, h bar over
This was I wanted to talk to some cold atom people. We were discussing, is the Mott-Joffe-Regel limit the same thing as E squared over H?
So this comes about when the mean free path is on the order of the interparticle spacing.
Yeah.
Then the mean free path actually drops out of the diffusion coefficient. You get something that's just h bar divided by the mass.
I
of
see,
the
yeah.
object.
So you're saying, can I take this diffusion constant and get a length from it, a diffusion length?
No, in fact, for the diffusion coefficient, the only thing that's then in there is only the mass of the object.
Yeah, I can get
So
you
you
a
get the
length.
mass of the object.
I can use that and get a length from this.
Mass.
Yeah. Yes, I can do that in 10
The
minutes.
units of diffusion is h bar over the mass. Hilariously.
Yes, right. I can get you a mass, or I can get a length. I've done neither of those things, so I will do both. I will do both. The length could be more interesting because then it's a question of what's sort of the diffusion length of whatever these objects are. And I can tell you right now it's going to be around a lattice parameter, something of that order. But let me do some arithmetic. If you have to go to the airport, feel free to leave. I won't be insulted.
So I'm confused. In which frequency range do you see that relaxation of dynamics? How low are the frequency?
Okay, it's yeah, below
Compared to KT.
this, it's here. So it's so KT ranges from 25 MeV down to around 10, and then we're looking at sort of minus 25 to 25, minus 50 to 50 MeV. This is the energy scale here.
So the energy scale is not much smaller than the temperature.
They're similar.
So,
Yeah.
So in that range, would you expect that you still have frequency dependent of your scattering rate?
Oh, and we do. Oh, of the scatter. Well, the response is frequency dependent. The scattering rate is constant. And so this is the point. So the frequency dependence comes from this, and then the tau is just in this gamma. So we don't need to invoke any additional frequency dependence in that.
We can't see your pointer.
Oh, you can't see my pointer. Sorry. Okay, can you see this thing? Yeah, so all the frequency dependence is in this omega over omega squared. This gamma is just tau to the minus 1. So this doesn't seem to be frequency dependent. But you can see the data are not amazing. They're not as good as optical data yet. So you might imagine later we might have to put some frequency dependence in this. But at the moment, we don't need to do that. But I think it's a higher order effect.
What's the lowest frequency? Sorry.
The what?
What's the lowest frequency that you actually access?
I mean, we go through 0, but there's a finite resolution.
Yeah.
So the resolution width is about 6 millivolts. So as you get closer and closer to that, it's a question of when do I stop believing the data, and that's what the shaded area. I'm sorry?
Down to where did you use the data for your analysis?
We fit everywhere except where the gray box is. So we fit this region here and above. And then below that, it just happens to look okay.
So like 10 million.
Something like that.
All right, well, let's thank Peter and all the speakers in the session.